All right, everyone, let's get the lecture started. Hello, hello. Come on, everyone. Can you hear me? Not really? Okay, one sec. Hello, hello. Can you hear me? Okay. Can you hear me? No? God dang. Let's see. Okay. Can you hear me now? Good? Okay, perfect. Yeah, let's get the class started. today we're gonna mainly go through the exam one as a review. I noticed a lot of people show up today, so good for you. Some quick agenda of today's lecture. We're gonna first go through some exam logistics, and then we can do it either way. I prepare a few slides. We can first quickly go through those slides to get the basics of content, and then we can look through the design problems and maybe other questions together from one of the previous midterms. Or we can do the other way around. Depends on, do you guys have a strong preference? Okay, no, we'll just stick with slides first. I will try to go through them faster so that we have more time to work together on the design problem and hopefully maybe one of the stack problems as well. Okay, midterm logistics. In case you haven't noticed yet, it's gonna happen tomorrow on 4:30 to 6:30 at these 3 rooms. And the assignment of the seating is based on your unique ID. If you are from A to C, the first letter of your ID. A to C, you go to the 1206, and then if it's D to J, you go to 1017. And then if it's K to Z, it's 1013. For those who need special accommodations, your exam time will be starting at 2:30 p.m. And then we're getting a room for that. Yeah. So any questions on this? Yes. Only for the special accommodations. Any other questions? Okay, perfect. And a few things more. It's going to be closed booked, closed note. We will be providing data sheet and reference sheet together with your exam, just like the practice exam in the past. The majority part, the 2 appendix will remain the same, and then the first part of the data sheet will be slightly different with the content that needed for the design problem specifically. And yeah, you can bring normal calculators. No graphics calculators are allowed. I don't think you would need them anyway. And then, of course, your phones needs to be stay in your pocket. No texting, no video calling during the exam. And we will try to make a timer inside of the room so that you can keep track of the time. We'll be posting the data sheet tonight so that we don't want to give it away too much in advance so that everyone kind of guessed what the design problem is. But we also don't want you guys to just jump in and see a big chunk of text during the exam. So we'll release the data sheet tonight. Yes.
Do we need a calculator? What if I don't have a calculator? That's not a graphic calculator.
If you don't have a calculator, I don't know. How good are you with adding, multiplying under 100?
X powers of 2, then 3 is fine.
Yeah, I think you'll be fine. Yeah, if you run into any issues, we're sitting outside. Just come talk to us. We can be your calculator. Okay. Any other questions? Yes.
Previous reference sheets available for the previous exams, for the previous practice exam, also the data sheet together.
Yeah, they will be together. So basically, the data sheet and reference sheet will be together. The first part will be the part that's specifically for the design problem, and the second, the appendix part, will be for other more general questions. Any other questions? Okay. Perfect. I see everyone is super excited. So some strategies here. Try to maximize your points. Do not get hang on any one particular problem. You should always leave enough time for your design problem, just in case that it might take longer. Just in case you don't have enough time to read through all the required register configurations or register address, all those informations. And you should clearly state any of the assumptions in the questions you're not sure of. If you're trying to write an answer, but that might or might not depend on some assumptions you need, just state that in it. And even if you get it wrong, we would try to give you some points back based on the assumptions you have. Also show your work and explain what have you done and your approach. Those again, for the partial credits, if you, just some strategies, just in case you got it wrong on the last step, but the previous steps are actually correct, then we can still be able to give you some partial credits. Exactly. So the data sheet, after this tonight, and then if you have any questions on practice or data sheet, please try to ask that on Piazza so that everyone can benefit from that. You're not competing with each other. We're all fighting this together. Well, you are competing with us, so not with your neighbors. And we will be, the data sheet might have some small editing until tomorrow, but I think so far we're pretty finalized. We will be just do another final pass after this lecture and then release it on the Google Drive. You don't have to bring it. You don't have to print it out. We will print it out for you and then hand it out before the exam, and that will be the latest version. So, yeah, and we will also tell you what we changed based on the version that we will be releasing tonight, and what's the difference between that and the final version, if there's any changes. Yes. Things to study. It might be a little bit too late for. Oh, not too late. You have 24 hours. So yeah. So homework and labs. All the exams on the website. In case you haven't seen it, we have posted 2 practice exams. We will be going through at least one of the design problems together today for the fall 2024. And then if we have time, we might go through one more register and stack problem. And questions are pretty much like homework and the previous practice midterms. Nothing fancy, no surprises, just, learn from the lectures and homework and previous midterm, and you should be totally fine. Topics to be covered, the instruction set, ISA, the ABI application binary interfaces, memory I/O, and also the interrupts and MVIC. The interrupt and MVICs will not be any of the longer questions. It's only going to be in the multiple choices and the short answers. So yeah, it's not going to be too complicated for you, but just make sure you know the concept. Today we'll be mainly go through the first 3 because the interrupts and MVIC we just covered in past 2 lectures. So, but if you have any questions regarding that, feel free to raise your hand or, okay.
What's the difference between APB versus the APB light?
For the APB light, I believe that's one of the assumptions when we do the GPIOs, we have the GPIOs to be as a 1 PB instead of as actually it's a AHB, like the high performance ones.
What was the question again?
Basically the difference between the APB and the APB light.
I still can't understand. What was it?
So can you say your question again?
The difference between the APB and the APB light that's on the slide.
Oh, APB light. Oh, okay.
Same thing, right?
Pretty much.
I don't know. I don't think there's a difference. There might, it suggests that there's a lot of subclasses of those peripheral buses, and it could be that there is some differences, but we're not gonna emphasize that at all.
Okay.
Yeah. You're welcome.
Okay, any other questions? Perfect. So let's first go to the instruction set architecture. Basically, this is what you will typically see on a instruction format. We have the labels, we have the mnemonic, we have the operation names, the destination registers, the first of the operation source, the second operation source, and then some comments. This you should be, if you took 370 before, you should be quite familiar with this. We are not going to be test you very heavily on this. I believe you might or might not be required to write some very short instructions, but not going to be a whole program, so to speak. Yes?
Is the label a number because it points to a place in memory?
The label is number because, so if you go to a actual what the register looks like, those are encoding, or those corresponds to which type of instruction it is. These things will be included in the datasheet as well, just in case you need to, yeah. So yeah, speaking of that, yeah, in the data sheet, we will have these instructions by bit breakdown for you, so you will know exactly which index within each of the 32-bit register corresponds to in a instruction. Yeah, those are basically just what's corresponding to it. And some of the things, for example, like the S label, that basically means you update some states flags that's being saved in the program stack registers. I don't think we're going to have any test on that either, but just something you should know of. And then also we have the W, which will enforce the instruction to be a 32-bit encoding versus like 16-bit encoding, etc. It's just a few bits within the instructions that tells you, which type of instructions it is. Because in our instruction set, the thumb2, we can do both 16-bit and 32-bit. Yeah, and the destination registers, source registers, and etc. All right, and in the registers we have in the core, basically all the registers are 32-bit, 32-bit length, and then the R0 to R12 are the 13 general purpose registers, and R13 is the stack pointer, which we used, I think, heavily doing like when we do like function calls or interrupts. That's where you push the data in the registers too, so that they can be saved once the program comes back to the previous location. And we also have the R14 as the link register. Those are the values saved for, again, basically the address you will be returning to if you are inside of some subrouting calls, etc. And program counter is what keeps tracking what's your current memory locations in terms of the programs, in terms of instructions you're running at. And some of the other special registers, the program stats register, those are mainly used in our case so far, being in the interrupts. So just be aware of that, and a few other things that might not be as important, but just aware that these registers exist, and then they're different from the R0 to R12. Any questions on the registers here? Okay, perfect. Okay, and the memory organization here, we have a whole 32-bit on each of the addresses, and then totally we should have a much larger memories, but in reality we only get allocated 4 gigabytes here. And it might be useful to just remember some of the index between like where each of the blocks starts, basically, so that you know which type of things goes to which block. I think that should be the only thing that's tricky, might be a bit tricky here. But in general, you should just treat like any blocks within this memory, it's basically treated exactly as others, despite if it's like external memories or external device, or if it's stack, or in later case, if it's peripherals. So they all treated the same inside of this MMIO system, in the memory system. Yeah. So again, each of the memory location have a 32-bit address, and each address location holds a byte. We usually do this by incrementing or decrementing 4 in terms of the address, so that a whole 32 bits is being loaded or stored within the memory. Any questions on this? Okay, sounds good. Yeah, just another thing is, know your Indians. We're gonna use the little Indians through the course, also the exam, unless otherwise stated. And I don't think we otherwise stated in this exam. So just, yeah, it's pretty much gonna be the little Indian for you guys. Yeah, this is just some like one more examples on essentially what the program looks like and how the memory is gonna be handling this. Basically, we have this on the left. These are the registers. On the right is the memories that's being holding all this information. In the middle, this is just like example programs that are running. In the first, we do like a move. Basically, we put this number 1 to the register 0, which is in the, let me see, here. In here. And then next, we do like a load from a memory number, which is memory address number that's stored in the register 0. And then we add 5 to that, but without changing the number stored in the register 0. And then later on that, if we do like a loop thing, and then we do the subtract. This is a pretty straightforward example here. The S here basically updates some of the flags here. In this case, if it's 0 or not. Any questions on this example? This is a very straightforward one, and it might be useful to. We'll go through this a little bit later, but might be important to know that when you do the load or doing some manipulations, what's the immediate add and which type of load that changes the register value, which types of them don't change, whether they change the pre to the instruction or after. But yeah, we'll get to that in later. So basically, this might be quite important. Just remember that. Yeah, and you have seen this architecture over and over again. It's going to be pretty much the same architecture we go through the entire course and specifically for this exam as well. If you have any questions regarding this flow, let us know right now. Or this looks quite familiar and good to everyone, hopefully, at this point. Yes?
Is there any chance that we'll have to be talking about age, peripherals versus APB?
There will be no chance in this exam.
Okay.
Yeah. Any other questions? Okay. Yes.
So there was a question on the exam asking about what drives the read data line and what drives the write data line. It was part of the short questions. I think the answer was for the read, I think it was the APB, and then for the write, it was the APB bridge. Can you explain the difference? And also, it said what module drives. Can you explain what a module is? So, for example, one of these areas is that it's called module.
Which question is this?
It's 1224 question 2.1 or 2.1?
Yes.
2.1.
It should come up any minute. Okay, perfect. So this was the question, right? Can you guys see this? Okay, so basically, what module drives the PRE data line? And then also the second question, which module drives the pSelect? Is that the question? These two? Yeah, okay. So yeah, so basically these data lines are the communication, they're within the communication bus that's being sending between the requesters and completers. So for the first question, we'll be just use APB here because that's what the, you can also do, because that's where the data was stored and happening within the module. Yes?
In lab, we do like a lot of GPIO stuff and GPIO signals, and we were looking at the PR data of the GPIO.
PR data, yeah.
The GPIO is
Yes, that's a very, very good question. So yes, so the technically the GPIOs are part of the AHB peripherals, but in the class and in the in the exams that we test you, we just assume then our normal HP, like APB here, so that it's simpler for you guys to work with. They essentially work with very, very similar like methods, like the mechanism is quite similar. It's just the AHB have much higher like speed requirement and more stable. Yeah.
So if we say AHB in a question like this, like on the answer key it says APB, would we get it wrong? Just because like if you just look at the data structure itself or the pipeline itself, you see that it's an AHB stuff.
That's a very good question. Matt, do you remember how we graded last semester? Do we give points for AHB for this?
Yeah, this one. Oh, so you can either choose what was our answer? I'm sorry.
Oh, this is basically APB.
Oh, we put APB.
Yeah.
Which module drives? That's true. And then, what did we say? So your question is,
He wants,
you could have
yeah.
answered AHB because GPIO said over there.
Yeah.
Confusion. Yeah. Yeah. I agree. I think we may have allowed that, and it is confusing there, because usually we always kind of look at peripherals through the APB. You know, we even suggest that in the lab context when we did the custom IO, we basically said, oh, it's similar to the GPIO we were working on earlier. So we kind of suggest that. But this is probably what really is happening, is that GPIO is actually looked at because it has the potential for higher capacity, and they can do that. And you also notice the EECS in there, so you might want more bandwidth transfer over at AHB. But in the context of an exam, it's probably always pretty safe when you're talking, in particular when you're talking about these signals, that you would be referring to the APB.
Yeah. Also, let me also add one more to this. So I think in this exam, the keyword we were looking in this question specifically, the keyword we're looking for is the peripherals. So whether you put APB in front or not, the peripherals will be the keyword we're looking for because it's a P-read data. That's where the data is coming from. And that's the module drive that. And I'll answer the second question first. So same here, which module drives the signal P-select? The P-select was the signal that's being, sent out or monitored or manipulated by the requesters. So the keyword we're looking here is requester, or you can call it initiator, or you can call it master. It's not the APB or APB bridge. It's technically correct both, but the keyword we're looking for is here peripherals and here requesters.
Yeah, because I think there's a P-select for the HB too, right?
Yeah, yes. So because technically they're both right. Does that answer your question? Okay. Yeah.
Lecture 4, there was a slide with the requester and the completer.
Uh-huh.
On the output was of the completer was P-read data, and it was going into the requester as an input. So if we were to say what drives P-read data, since it's the completer, it would be the APB peripheral because it's on the output, right?
Yeah. Yeah. Yeah, I believe if you answer on completer, we will probably give you points last year as well. Okay. Any other questions? Okay, yeah. Oh, sorry. Uh-huh. Uh-huh. Okay. The question here is about the 2.3 and 2.4. So basically, these parts are covered in the lecture when we talk I think only 2 slides within the compilers, like which the compiler versus assemblers, basically which part of these are, which type of these files are being generated by which one. And then, yeah, we're not gonna test you guys too much on this one, but it's good to know that where those things are stored in the memory. Okay, let's get back to the, okay, cool. So yeah, just to have like one more example, we can go through this quickly. Basically, we have a load function, read at the memory, read at the value stored at R0 as the memory to load from. And then that will give us basically to that address and then put that inside of the destination register R1. And this is, and every time, we write 4 bytes. So, and based on the little endian we have, this is the answer we're gonna have in the register 1. And then later, if we do like offsetting, basically we will add 4 to this register. And then so that instead of accessing the 000, we're now accessing the 004. And then we do, again, 4 bytes, and then we load that into the register 1. And that operation does not change the value inside of the R0. And in another hand, this is what does change the R0. Basically, we would do the immediate add first with that little sign there. We do the immediate add, and then we access the updated R0 as the memory address, and then we load the whole 4 bytes, and then we put it in our register 1. So those two commands basically result in the same content being loaded from the same address, but the register number, the register number R0 is being changed, the one that stored the address, memory address. I hope, any questions on these two? Basically offsetting versus pre-indexing. Okay, perfect. And then we also have the post-indexing. So it's, in this case, it will still look at the same address that's stored inside of the R0, go to the memory, pick the corresponding content, load it back, and then add 4 after this is finished. So this is post-indexed addressing. And this is like a very useful summary that you can just memorize that. Any questions on this? Yes.
Say we're doing like an assembly question, like developing like an assembly problem.
Mm-hmm.
How would we know when to like choose which of them? If we have
The question is if you're trying to write a assembly program yourself, which one you want to, whichever one that works. So yeah, you don't have to worry too much unless we ask you to write the shortest one, but we're not going to be that complicated in those type of questions. Any other questions regarding the post-indexing, pre-indexing, and then offsetting? Okay, perfect. So next, we're going to go through the ABI first, the application binary interface. So basically, this is for when we do like subrouting calls between different functions. Some general idea here: the subrouting call must be preserving the context of the register R4 to R11. This is for the callee saved. For the R0 and R3 are the caller saved. So basically, whenever you enter a subrouting, the caller needs to push these things onto the stack so that when it gets back, it will pop it back and it knows where it was left over. One of the more special case is the R12. It's another general purpose registers. We covered that in the interrupts. That's also one of the registers that holds like some temporary members, and it is also caller saved. Basically, it's used a lot of times to be kept in, if you do like some more complicated add or multiplication, those are the registers typically used to hold the temporary or intermediate results. So that one is also caller saved. So just one special case on the R12. So any questions on this? Callee saved registers? Okay, perfect. Let's power this through. And yeah, this is also just like a diagram to show you each part of these registers and whether they are saved or not, and whether you use that for either whether you can freely use that during your functions, or whether you have to store them first before you use them. For example, the Kali saved ones, you have to, if you want to use any of that, you have to make sure you store that you push that into the stacks first before you can use that. Yes?
So is R9 color or Kali saved?
Which one?
I was going to say, is R9 color or Kali saved?
Oh, yeah, R9 is one of the, R9 is one of the special ones. So typically it was used as like static base register. It's point to position independent data. So we are not going to test you on this one. It's normally you will not use this for your program, but it is considered as a Kali saved, technically. If the Kali still wants to use that, you should still save it. Yes.
Registers pushed to the stack in the order that they appear in the instruction, or always in descending order?
Sorry, can you say it a bit louder?
Registers pushed to the stack in the order that they appear in the instruction, or always in descending order? So if you try to push R5, R4, does it push R5 first?
Yeah, it's always it's stored itself. It's always in descending orders. So you push, say you have like R3 to R0, you push the R3, and then you push the R2, you push the R1, and push the R0. And then when you pop the R0, and then pop R1. And when you do that, you decrease the stack by 4 and then push it in. And then you decrease by 4 and push the second one, and that. And when you pop, it's just the other way around. But the order is always determined by the index number in front of the register, no matter how you put them. Any other questions? Okay. Does that answer your question? Sorry, I think. Does that answer the question? Or you have any follow-up? Okay, perfect. And this is, a quick graphics to show that how the subroutine calls happens. Basically, you have like a branch, and then that points to a function, and then we will store whatever that's needed to be stored, and then if we have like multiple subroutine functions, when that happens, even the link register was not enough to hold, because it only can hold one value, right? So even the link register will need to be pushed onto the stack in order to have the program able to find its way back to like 2 layers or more than 2 layers. Yeah.
Are we allowed to pop into the link register? We were told at one point that we weren't.
Are you allowed to what?
Are we allowed to pop into the link register? Is that one point we were told not to?
Pop the link register. So if you if you saved the link register to the stack, you can totally pop that. Also, when you write assembly code, you have a lot of freedom. Technically, you can do anything. It might result in some, undefined behaviors within the program. But yeah, for the link register, you should always you should only pop them if it was pushed at some point, and then you make sure you pop them in the correct order, so that every time it knows where it's to return to after the subroutine call ends. Yeah.
Is there a difference between doing pop LR and then BXLR versus doing pop PC after you push LR?
So the question is there a difference between you do the pop LR and then BX LR? Yeah, so this pop LR here is basically updating the link register value here, so that when this branch happens, it knows what was the correct address that's returned to. If you don't do this pop, it will be popping back to, in this case, the quad again.
I think you're asking if it's okay just to pop into the substitute.
Right.
So after the BL, you ask you just pop to the EC. It's kind of a shortcut.
Oh, I see. Yeah, but it's not recommended, I think. I think usually, I don't think that's recommended. But I think technically you could do that. Yeah.
Yeah, he's asking because we do it.
Well, you guys do that in lab? Okay.
It's our fault.
All right, no worries. You can do that, I guess. Any other questions on this? Okay, let's go to the next one. This is also like another quick example. We ran through this in class. Do you want to go through this one more time, or we save some time for the exam question? Go through this? Okay, any other? Should we go through it one more time? Okay, great, let's go through this one more time. So basically, currently, that's where the stack pointer is pointed to, somewhere in the memory address. And then the PC, the program counter is currently at the 13138, so which is here, if you can see my cursor. So basically, it points to that, we executed that one, and then that will put a number 2 into the register 0, which get updated here. And after that, we do, if it like to do like a branch jump, and then in this case, we will put the previous, so the current PC value plus 4 into the link register. So the next steps. So basically where it comes back. And then we preserve the link register. And then we goes to the quad function, which goes to, well, it does the push to the stack. So we push that to the stack. So the stack will decrease by 4 and then put the value there. And then it will jump to the SQ function here. So it will do that, and then save this, basically the next step of, where's my cursor? Of the previous PC location, adds 4, and then store in a link register. So that we know that's one level back. And then we goes to where this SQ points to, which is the 144. So far, so good. This is where we already have now 2 addresses we're going to returning back to. One in the stack, one in the link register. The order that we do this is always we go to the link register's value first, and then we pop it back to the link register and do another layer of going back. Okay, what's the question?
I just want to make sure, the reason why we want to stack pointer because we push LR is why, like we go from 0x2 1 to 0x1 FC or I, why do we do that?
That's because the instruction here push LR. Yeah, that basically push the value stored in the link register onto the stack. And then it does another exit, and then which will go back to the previous address, basically cost whatever was saved in the link register, go back to the program counter. So that this is one level back, and then the PC look at that address and realize that we're going to have to go back to that location one more time. So we take the current PC value plus 4 and then put that into the link register one more time, and then we go back to that multiple instructions one more time. And then we do that. That also updates the value instead of the R0. And after that's finished, we will basically do the exit one more time, look at the value instead of the link register, which is 158, and then go load that into the PC program counter, and then goes to that instruction in 158, which popped the link register value, previously link register value that we stored inside of the stack. So that will cause the stack pointer to basically pop it and increment by 4. So that number is now loaded back to the link register, and then basically we will branch to what the link register was, and then switch that, which points to the end of the program. Any questions in any of the steps in between? This is like one of the slightly more complicated example where we have more than one subroutine calls. so that we have to store even store the link register onto the stack. Any questions on this? Yes.
What's the difference between BX and BL?
Which one?
The BL instruction and BX.
What? That's a very good question. Let me check the data sheet. I think so. The B is branch, and then X is exit. Let me check the BL.
What, your question was the difference between BL and BX?
Yeah.
Oh, well, the BX, yeah, I don't think you can, oh, that's a good one, I don't know if you can BX to a label.
Yeah, I think BX usually is just the average.
I don't think you can. Yeah, the nitty gritty on that, I'm not sure. But you can't BL to the LR. You have to BX. That's fair. And there may be BX may have some other implications.
Yeah.
But I
So.
can't remember all the details, but you always BX BL, and you always branch and link. That's what you know.
Yes. So basically, the BL, the L stands for label. So that was basically branched into a subroutine at the label, which is the SQ. That's the name of this subfunction, or like the label for this subfunction. And the BX here is branch indirect to location specified by register. So in this case, the LR is a register, so we use the BX. That's a very good question. And then all of these information, I just checked the datasheet. They're all included in the datasheet. They will tell you exactly what's the small differences between those second or third labels within each of the instructions. Any other questions?
So can you BX into other registers?
I think so. So let me show you so this is the datasheet. So basically, it says here, BX is where you, by RM. And the BL is for the labels. Yep. Okay. Any other questions? Okay. Okay. First.
So on the data sheet, will like the like character modifiers for some of the instructions be on there?
The what? Sorry.
It's like for the like add with flag and stuff like that. Will that be on there?
I think so. Load add. Yeah, all those flags are also included in the data sheet. Yeah.
Could you clarify again if we're allowed to pop the LR or not? Because I thought we were supposed to pop PC. You know what I'm talking about? Like we have.
We're not supposed to pop PC. We're supposed to pop LR. Ooh, sorry. Why are we popping PC?
Because in lab, I thought we were told not to pop LR, which I thought we just talked about. Also.
Did somebody tell you that?
It said in the lab docs not to pop that large.
Really? Oh,
Yeah.
I gotta fix that. Because I think it's equivalent. So pop to PC, if LR is in the right position, will.
Yeah.
If the stack is in the right location, LR, it'll pop LR into PC.
Which will be equivalent to branching to LR
And pop.
and pop.
Yeah. So it's functionally equivalent.
Yeah.
And I think what he is saying though is you just gotta be careful about, is it in the right stack position to do that?
Yeah, because you always have to make sure it's right at the last layer. You can do that. If you have multiple link registered, multiple layers of subroutine calls, then that might cause some errors.
Okay.
So yeah, pop only if you pushed it somewhere before. Okay, let's go to the next part. So MMIO, we kind of covered it across the slides, but let me just push this through faster. So basically, two basic types of the memory mapped. First is like port mapped, which is very common inside of like general purpose computers. They have like a port specifically at a location. But in our case, the embedded system, the Cortex-M, we use this MMIO system that basically has a memory address assigned to all the ports, peripherals, external devices, if any, and then treat them all the same as a memory address. So it's more convenient and more simpler for us to interface with any of the I/O devices. So this is like from like a higher level to what is MMIO and why we do this. And yeah, so even this example is for like a GPIO. Even for like GPIOs that do input or output, that we still treat them just like a memory space inside of the eyes of the core, basically. Everything is just load and store. And if you want to have a value to be output or interact with any other external devices or external peripherals, you just write to the corresponding registers, and then that will be triggered, just like accessing a memory. Any questions on this? Yes?
For like memory maps, input and output, you said that each device register is assigned to a memory address in the address space of the microprocessor. It's not the address space of the core, right? It's like other region of the microprocessor.
So remember, like previously, we have 32 like a register that's assigned to the whole memory space. So in total, we could have like 2 to the 32 times 32 bits as the whole memory. That's basically what's the view from the core or from the microprocessor. If those space exist or not, that's not what the core is concerned. It would just treat everything the same here. Any? Does that answer your question, or any other questions?
Yeah, I'm curious about like.
Or if you have any specific questions on the exam.
Like in this framework in the pipeline, there is like a memory interface in the core, so I'm not sure like what that refers to.
Is that the data sheet or?
Question 2 for 2024.
2024. Okay, let me switch to this. Which question again? Sorry.
Yeah, that's one. So there is like a memory interface in the green box, like core.
Memory interface. Oh, you mean here?
Yeah. So what that refers to?
You don't have to worry about that. But yeah, yeah, you don't have to worry about that. Okay.
That might be the FMC. There's a flexible memory controller.
Mm-hmm.
It might be, yeah. But yeah.
Okay.
It's a whole. It actually can map some of the address spaces out through special range. And, but you don't have to worry about it.
Okay. Any other questions? Okay. Cool. Let's go to the GPIO port. Basically, this is a diagram that indicates how it works underneath. We have GPIO ports that just are stacked alongside together, so that they make each one bit consider one of these structures underneath, and together they make one GPIO port. And I think what's more interesting to look at is basically, oops, not this one. Yeah. So in this case, we will have like each bit that's assigned to any one of these, and then together from like one level up, the core or like the masters or requesters will basically look at one registers and know what's the output or what's the bits to write into each of these specific GPIO pings. And these are determined later on. We would iterate on this basically based on the P address that's within a peripheral. So if you have, this is a case where you have like multiple registers within a peripheral, so that on top of the P enable and P select signal, you also need a P address to know exactly which register inside of these peripherals are the ones you need to access to, or write to, or read from. Okay. And a little bit on the pull up, pull down, and open drain mode, or circuits in this case, that's within the GPIOs. The The pull-up basically will, if you look at the graph on here, it ensures a default high because it's measuring at this point. So if this switch is open, it will basically read the value from the BCC, and then if it's closed, then it became a 0. And on the contrary, on the pull-down registers, if the switch is open, then basically the reading will be 0, and when it's closed, the reading become 1. That's pretty much as much electronics you need to know for this exam. But if you have any other questions, please raise your hand. Yeah. Open drain basically it's kind of like a floating state. Usually, if you so basically the GPIO can only pull the line to low. In this case, you cannot you cannot drive it high. So usually we use it in the output mode, I think. So if you do need if you do need like a high, you need some external power to do that, and which is what's typically used for this open drain is that, for example, the core is running on 3.3, right? And then whatever stuff you're connecting to or trying to control is running on a different voltage. So instead of that drawing a lot of power from the core, from the microcontroller, they have like additional maybe pull-up or pull-down circuit, or connects to like additional power that supports the power to that peripherals. That's what most of the time what the open drain was used for. Sometimes they also use that to protect the connected device in case it got accidentally broken. But yeah, any other questions regarding? Okay, perfect. And then yeah, this is the maps for the GPIO registers. They're gonna be put inside of the peripherals. So basically, from the address 04 0000 to 06, 0x6000. This is the range of the where the peripherals are stored at. Yeah, it might be useful to just know these numbers. It will be provided inside of the datasheet. So, but in case you asked where you should write this thing into, yeah, pick a address that's within the range, and it should be good. Okay. Cool. And this is just like a diagram showing how a store would look like from the architecture point of view. Basically, that value is being stored just as any value that will be stored inside of the memory, but just because it's being stored into an address that's corresponding to the output register of this GPIO peripherals, so that all of a sudden became the actual output on this pin, which interface the outer world. But yeah, basically everything is treated as the memory address. All you need to know is which blocks corresponding to which. And yeah, this is like the diagram that will be included inside of the datasheet as well. And in the class, we also went through 2 examples. One of them slightly more straightforward. Basically, we have 1 requesters and 1 completers, and how do we connect all these wires, all these signals between them. And we also have, we'll also provide you with the register details. This will be quite useful inside of the design questions. Just make sure you know which type of registers whatever the device you're interacting with provides, and what's their address, and how the bits allocation works. Like, essentially, which bits are the data you're supposed to write into or read from. And when you draw the diagrams, these are some standard notations. We'll also include that in the data sheet. And the more complicated example we talked about in the class is this one. So the previous one is just one of them. This is have like 3 different registers within a GPIO. So they have the mode controller, the out register, and also the input register. Let me just give out all the answers. I think we ran through this in the class, but any of these lines feels not familiar to you, or you have questions? Yes?
Can you go back to the GPIO
This one? This one? This one?
Actually, okay, so my question basically is in the data sheet, it shows like how to interface with the motor and then the GPIO, but it doesn't say like GPIO A, GPIO B. Are those going to be given in the questions?
It will be given in the questions. Normally, I think in the design questions, you probably only have one GPIOs to interact with, right? One GPIOs to interact with for most of the design questions. But we will give you all the address. Yeah, we'll give you all that. So let me just push through all these, and so that hopefully we can at least go through the design question together. But any questions regarding this figure? Yeah.
Yeah, for like the mux.
Yeah.
Even though there's only like 3 inputs, why do we need like all 3 like I guess like AND gates in the mux when there's only like 3 inputs?
That's a very good question. So I think technically in this one, the reason is, so each output from this is 1 bit 1 or 0, right? And then it used that go here so that it tells you, it only look at the one that with the ones, if that makes sense, because they cannot be both on at the same time. So technically you only need 2 bits for this, but you will need additional logic gates here to handle that, because these 3 signals can only be on one at a time. Yeah, but they are also, we will go through that in the design question. You can also, if you only have 2 of them, imagine, you could just come to them with 1, because it's either on and off. So yeah. Any other questions regarding this? Okay, I'm going to move on to the next slide. Okay, perfect. And this is like basically a example of when we have 1 requesters to control multiple completers. We went through this in the class, but basically what's important here is, or what's good to know, that the write data goes to all of these peripherals, and the address will also go off them. The only different one is the p-select. The p-select will only goes to 1 peripherals per peripheral. All others like p-enable, p-write, p-address, all these things are shared between peripherals. And do not get confused between this and this one. This one is within a peripheral. We just have multiple. Registers. So that's why just by p-select, we do not know which one of these registers are turned on. That's why we need the p-address, additional bits. Yes?
Yeah, so just to get it absolutely clear, p-select tells you which peripheral within a module to select, and then p-address tells you which device within a peripheral to select. You can understand like that. More accurately, the p-address give you exactly the address, and they just happens to be gonna be within this peripheral's address range, and then that will give you exactly which register within this peripheral that goes to. But you can pretty much understand like that as well. Yeah. Any other questions? Yes.
Why do you want to go for like a double wire sense?
What do you mean double wire?
Like how there's different forms of like wires?
Oh, if the signal have like more than 1 data in it, more than 1 bit in it, yeah, that's why. That's when you're going to need that. Okay, so this is like what the image will look like for that instruction. Basically, all of these are the same except for the p-select. The p-select was on only for the A, and then that's why it happened. This instruction only happened on the GPIO A. And the p-ready here also only going to be sent from the GPIO A to the requesters, because the p-ready is the signal that's derived or that's being provided by the peripherals. That's indicating that I've done my instructions and ready for the next instruction. Any question on this? So basically, the p-ready and the p-select are the special ones here. The rest should be pretty straightforward. Okay, and then, perfect. So those are the slides. Any of the, okay, yeah. If we were what? Yes, yes, we'll be going through the design question of the 24. If you guys don't have any question on the slides, like the lecture content, we'll go through a design question together on the, so does that sound good? Okay, perfect. So this is the design question from 24 and for the wireless distance sensors. So before we go through this, let me show you something quite important. Basically, how would you read like a data sheet, right? So this would be something similar. Basically, it provides all the pings on each of the device that we would be connecting to. Those things will be more useful later on in your actual final projects and stuff. But read them through, understand each of what these pings are. You are not going to be heavily tested on how to connect these pings from like a PCB or circuit perspective. But it's good to know what these pings stands for. And then sometimes in this case, it tells you how the result is calculated based on reading of the registers. So this is probably something pretty useful to look at. Hopefully before the exam. In this case particularly, it basically tells you once it's read this distance sensor time flight. Once it's read the signal, how do we interpolate that signal into a actual number, which is how many meters, what's the distance. And next would be another modules, in this case, the wireless transfer module. Similar things on the first page, gives you like a pin out diagram, and then which each of the pins are. It lets you know how many GPLs you have, etc. Chances are we probably only going to test you 1 or 2 GPLs. We're not going to make it like super complicated but these things are what the most important stuff on actual data sheet. These things are typically put within like the first 2 pages of the data sheet. This is just, we're going to include that. Let me go down, and here it tells you, in this case, it tells you what's the how do you interact with any of these devices through which registers. In this case, it tells you, for example, this radio control register. It gives like 3-bit fields on the mode that you can configure it into different modes. And also, I believe there's a send bit that's being So it tells you the send bit has to be in a state, otherwise the input to that it will be ignored. So in case you need to do anything with that peripherals, always make sure all these pre-requests are met in order for the device to perform the correct instruction you assign it to. And these things are going to be very important. So basically, typically, we provide you with a few registers. Here, we provide the control register, data register, etc. It's good to know the exact address of them, so that later on, when you look through the time diagram, you know which register it's been writing or reading from, so that you know what the program is trying to do. And it also give you different modes. Here, tells you, this is on channel 0, channel 1, channel 2. So these things are probably going to be pretty handy later on as well. Similar things for the other devices. So this is, I'm going through this very fast so that we have more time on the actual problem, but this is how you typically will go through like a data sheet. Does that look reasonable to you guys? You have more time tonight or tomorrow before the exam to look through, but these are the things you should probably pay more attention to. Okay, perfect. Let's switch to this. I hope you guys already read the questions on this one. Basically, it's trying to draw a complete diagram for the radio peripherals on this microcontroller. So when we look at this, can you guys see it? Okay, perfect. So what's the first thing we usually connect? Yeah. Yes, exactly. So we have the clock here. You can just do like P clock, and then sometimes I just connect these to P clock, so that we have more space. Clock. That's all good, right? And then what's the next? So for example, if we look from the top here, where the P read data is going to come from between these two registers. One register is for the D flip-flops. One of them for the control. So which one is this one going to come from? The P read data. It's probably going to come from one of the outputs from the D flip-flops, right? And that will likely also come from what's the input of this radio modules, right? Do you guys have any question on this? Yes.
Could you repeat where you said where reading from P-read data will be connected to the input from the radio module?
Yes. So you will notice that here there's a 32-bit data in on the radio module, and then we have also the P read data, right? So chances are we're going to read from multiple places. So what are those pings going to be corresponding to this P read? Which registers we will need to read from, and also what are other signals that we're worth reading from? In this case, probably pretty straightforward, hopefully pretty straightforward. We're going to definitely read from this register, right? We'll probably...
Why do we want from this? Why is that even specified?
We want to sync our inputs with the clock.
Yeah, but why is that register? Why do we even need that read data? What specifies that read data? Why do we even need to do it? If you go back and look at that data sheet, we need a register that's 32 bits that is labeled read write. We can have a register that's just write or just read, but that one's read write.
Yep.
So we need a read data. And I think the other one, the configuration register, the 4-bit, I think that's read write too. And then what else has got to be read? The device, radio.
Yeah. So basically, if we try to draw it out, this will also be something to be read from, and this as well. How are we going to handle, we only have one 32-bit bus here, but we have more than one input. We will label here, so this one have like what, 3, 1, 3, 0. This one, these two are all 32-bit.
Yeah, and label the address lines.
So chances are we're going to have a mux here, right? But how do we decide which one of them actually got triggered? We can figure it out later, but chances are there's going to be some select pings here.
You got to be able to select.
Yeah. Oh, sorry, yep.
Can you clarify why we're reading from, for the radio module from the input instead of the output?
From the radio module, the data in. From the output, where's the output?
Is that
There's only one input, the data in, yeah. So imagine you have a radio module that gets the data. This data has to be passed to the core, right? That's why we need this to be put onto the P read.
well, maybe that's not correct. Because maybe if we go back and look at the register description for the radio line, can you throw that in your data sheet? Is that because you might have
Oh yeah, that's a good point. Let me switch back to the...
That's your reference. That's data sheet. It's going to tell you what everything is. We go up to the radio line.
send.
Those bits needed, and then if you go down a little bit more for radio data. So radio data looks like we want to rewrite that too. So you're right. Right, we want to be able to rewrite that the data register associated with the radio data. So that's a little, that's the specification. So that's a little crazy because if you go look at the DN, it says DN. So let's go back to that page. No, go back to the design drawing. These are the only registers associated with the radio line. Yeah, go back to the example. That's the solution. Yeah, so now, but now look, so DN is actually being driven by that 32-bit register, right? There's coming out of Q. But what else are we doing? We're tapping it and bringing it back into DN because the register specification said we need to do that. We might not even use it in the application that we're going to do, but the register specs said we should do it.
So the end of this case is both read and write.
Say it again.
Oh, sorry. So the end of this case is both read and write.
Say it again.
So the end of this case is both.
DN, yeah. It's more than just, yeah, it's that register back there. The data register for that device in the specs that is going to be read. So we have to implement those data registers.
So yeah, basically, since this is read and write for the radio, we will have the additional line here, basically connecting the output from this 32-bit register, which presumably the P write data is going to go into, and then connect that with this data pin as well.
Yeah, so
and they will together.
Rewriting that 32-bit register, not
So yeah. Sure.
What if we don't have rewrites, like the spec?
What if we don't have one?
We don't have the rewrites from in the GPIO, like the spec. We need to do the input that to it.
What if we don't have rewrite? Yeah. What if we just have or write? Yeah. In this case, if that was only right for that register, then you wouldn't need that read.
Yeah. And if it's read-only, then chances are the D here is going to be connected to some other external stuff instead of connected to any of the writing P-write data bit, if that makes sense. If it's read-only. Imagine if it's read-only, probably this D is connected somewhere here. It will not be connected to the P-write data. If it's write-only, then this Q will not be connected to the P-read data in any way. Wait, which question are you referring to? Is it during the lecture or during the lab? Mm-hmm.
It's right, but we have to read the data back to know what we're writing. Data one right.
I'm not sure what you're referring to. Can you come back to me after the class, and then we will figure that out. Okay, let's get through this first. And then, so basically, that kind of gave away where is this P-write data going to go into. It's, chances are it's going to go to the 32-bit register because that's where you write into, and then that got passed down to the data in the radio module when this happened. And what's the other place this needs to be? This is the only part where the data can be write into these peripherals, right? So this is, chances are this going to come connected to this one as well. But this is 32-bit, and then this is only 4-bit. What do we do about it? You will check the register in the data sheet, and it will tell